Okay, so we're going to talk about a little bit about probability distributions here at the beginning, and then we'll move on and discuss something called binomial distribution, which is just one of many types of probability distributions that exist. So when you get further into probability, like if you're taking the stats class here or one in college, you're going to hear a lot of talk about random variables. Okay. A random variable is a variable whose value is determined by the outcomes of a probability experiment. So it's kind of like, okay, this random variable, I could calculate the theoretical probabilities for the given outcomes, like rolling a die. The probability distribution is a function that gives the probability of each possible value of the random variable. The sum of the probabilities in the probability distribution must equal 1. So that's pretty important. I want to highlight that or underline. Okay, so like the probability distribution is really just a way to organize all the different outcomes that are possible for a given event. And when you're done with the probability distribution, a really handy thing to do is make sure that all the probabilities in the distribution add up to 1. Then you know you haven't missed any probabilities or maybe overcounted any probabilities, like in case you had an overlap of some kind. I know next year in pre-calculus, any students taking the pre-calculus course, you will create your own games when you cover probability, and you will create a probability distribution. So that's something I always encourage my pre-calc students is make sure that your probabilities add up to 1. If not, there's an issue that you might want to look for. Okay, so we've got an example of rolling the dice. Is that already printed all out for you, or do you have to fill it in? Okay. So this would be an example of what a probability distribution chart could look like. X, that's my random variable. So the random variable is going to basically be assigned all the possible outcomes in that probability experiment. If our experiment is about rolling a 6-sided die, the possible outcomes are 1 through 6. So we have to assign the random variable each of those values, 1 through 6. Okay. And then the second line of your probability distribution, you've got your random variable, is where you assign your probabilities. So it looks like P of X. And we already know from our work that if we're doing rolling the dice, we've done a few different experiments with rolling dice, that should come out to be 1/6 for each of them theoretically. And I've mentioned this before as well. Whenever in a probability distribution, all your separate outcomes have exactly the same probability, 1/6, 1/6, 1/6. We can call this a uniform distribution. So, like, we're going to talk about the binomial distribution in the last half of these notes. A uniform distribution is another type of probability distribution where all the probabilities for all the outcomes are the same. And then just to kind of go over this part right here that I underlined, the sum of all the probabilities in the experiment must equal 1. So I could look at my sums here. I have 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. Of course, we would already believe that is 6/6 or 1. So we're pretty well convinced that we've calculated all the probabilities. We're not missing an outcome or overcounting something. Okay, so we're going to do an example where we create a probability distribution for a spinner. Okay, so it says the spinner is divided into 3 equal parts. That's important so that whether I'm landing on a 0, a 1, or a 2, they all have probability of what? 1/3, because it's all equal. If we separated the spinner into non-equal parts, we would have to calculate areas. Let x be a random variable that represents the sum when the spinner is spun twice. So I'm going to say x equals the sum for 2 spins. So part A says make a table and draw. This is called a histogram that we're going to do next, showing the probability of the distribution for x. So first we'll start out with a table. So if I spin the spinner twice, what are the possible sums? What are the possible random variables? Okay, I've got them on that first line. I could do 0 and 0 for 0. I could get a sum of 1, a sum of 2, a sum of 3. And if I did a 2 and a 2, the highest one both times, I could go up to a sum of 4, right? That would be my highest sum. Okay, so we need to figure out how many ways we can actually get these sums. So now it's sort of like we're treating it like sample space all the way back to the beginning of the chapter. So think about, like, what are the ways that you can spin the spinner twice and get a sum of 0? 0 and 0. And that's really the only way to get a sum of 0, right? If you spin any other number, your sum won't be 0. Okay. So how many outcomes are possible? 1 way to get that. Okay. So if you need to jot down like where that number is coming from, it's because you're spinning a 0 and a 0. How many ways can you spin the spinner twice and get a sum of 1? 2, because I could spin 0 and a 1, 1 and 0. Okay, so there are 2 possible outcomes for rolling, or for spinning a 1. Okay, well, how many ways can you spin the 2 sum? 1 and 1, 2 and 0, 0 and 2. So there's 3 ways to get the sum of 2. What about a sum of 3? 2, okay, because it would be 1 and 2, 2 and 1.
So order doesn't matter, or it does matter for...
Yeah, because if I'm spinning, like I'm listing basically all my sample space without, like one at a time for each outcome. But if you're spinning, like you could have landed on the 1 first and then landed on the 2. And that would be different than if you got on the 2 first and you landed on the 1. Yeah, order matters. Okay, and then 4, how many ways? Should be 1 way to get a 2 and a 2, right? So how many different outcomes are possible? What's that? 9. Yeah, we just counted them all up, right? Without listing the full sample space, by thinking about each individual outcome for x, the different sums, we've said there's basically 9 different ways for us to spin this spinner. Okay, and wouldn't that make sense? How many outcomes are possible when you first spin the spinner? 3. And the second time you spin the spinner? 3, and you should multiply them by fundamental counting principles, so there's 9 total outcomes. So can you do the probability of each of these? Yeah, it'll be 1 out of 9, 2 out of 9, 3 out of 9, which I would reduce if I was writing this out for a final answer is 1/3, and then 2 out of 9 and 1 out of 9. But if you add up all those probabilities, they'll equal 1, which has to be true in a probability distribution. Okay. I did not leave myself a lot of room for my histogram. See how it says make a table and draw a histogram? So I'm going to squeeze in a histogram down here. Thanks, Brianna. Let me see if I can move this. I'm going to squeeze in a histogram. Do you have space for a histogram in your notes? Maybe off to the side? Oh, you got a space, right? Okay, here's what a histogram is. It's kind of like a bar graph, but it's a little bit different. Okay, so I'm going to have a horizontal and a vertical axis. On the horizontal axis, you're going to like list out what are your possible outcomes. So they're like the different values or the different things for your random variable. So our random variable, remember, x was the sum of spinning the spinner twice. So our sums were 0, 1, 2, 3, and 4. If you put the outcomes on the horizontal. And then in a histogram, on the vertical axis, you put your probabilities, which I'm going to go ahead and label P of x, because that's a random variable x, so the different probabilities of my random variable. What's the highest probability you could ever have on that vertical axis? It's a probability. The highest one possible would ever be 1, right? So when you're like scaling your vertical axis, it's going to be a lot of times decimals or fractions, so that it's got to be less than 1, right? We could look at our decimals or fractions, and we don't go any higher for any specific random variable more than 1/3. So maybe I'm going to go with like, I'll go 0.1, 0.2, 0.3 right there. So I'm going to scale by 0.1. So you can choose your scale depending on like how high one of the probabilities is. I don't need to go all the way up to 1. And then what I do is I draw the bars. Now what's different about this than like an official like bar chart, if you did a bar graph in Excel. In Excel, it would have like the different bars and they're just separated. They have spaces between them. But in histogram, we put all the bars right next to each other so they touch sides. So 1/9 is like what, 0.11? And 2/9 is 0.22. And 3/9 or 1/3 is 0.33. And we go back to 0.22 repeating and 0.11 repeating. That is a histogram. It's like a bar chart, bar graph. It's different because the bar should touch. That's our histogram. This chart right here, this is our probability distribution. So it looks like a chart, the probability distribution. The histogram is just a way to visually represent that. This particular histogram we could describe, you know how I said the rolling the dice was a uniform distribution? This one we could describe the distribution in the histogram. We can see it real nicely. It's symmetric. It sort of mirrors itself. And sometimes you can describe histograms as symmetric, even if they aren't like exactly the same on both sides. Like ours does mirror itself, 1/9, 1/9, 2/9, 2/9. But if they were pretty close, you can still say that it's symmetric.
For the histogram, can you use fractions for the?
Yes, for the vertical axis. Yeah, if you wanted to do like 1/9, 2/9, 3/9, that would be fine.
Okay.
Yeah. What we're going to see later on is they're not going to be nice numbers anymore, so I just used it. Okay, any questions so far? All right, find the probability that in this particular example, when I'm spinning the spinner twice, I get a sum of at least 3. What does that mean, a sum of at least 3? 3 or more, right? So we want the probability of at least 3. That's 3 or 4 as possible outcomes for a random variable, right? And or means what? Add. So I'm adding the probability of 3 plus the probability of 4. There shouldn't be any overlap because I either get the sum of 3 or I get the sum of 4. I can't get the sum of both. Okay. And you can do it one way or another. You can go to your probability distribution and pick out 2/9 and 1/9 from the table. Or you can look on your histogram and you can look right there. This one here is 2/9 and this one here is 1/9. So I'm going to add up those two bars. So that's going to be 3/9 or 1/3. And then letter C, what's the most likely sum? 2. Easy way to pick that out is looking at your histogram. It's the tallest bar, right? The tallest bar of the histogram is going to be the most likely outcome. So you should say something like 2. It has the highest bar. Which means it has the highest probability. Okay, so if you take a Prob and Stats course, okay, you're going to be really interested in these distributions, what their shapes look like. And like this one is symmetric. That's going to lead you into something called a normal distribution or a bell curve, if you've ever heard those words. You can have other distributions where they call them right skew or left skew, where the majority of the probability is on one side and there's like this long tail, like it's really unlikely over here, or it's really unlikely over here and there's a big probability somewhere else. And those are things that you would study in a Prob and Stats class. Okay, turn that page. We're on the last page. We're going to talk about binomial distributions. The previous page is just like an intro to distributions. Okay, X is a random variable. You name it for all your outcomes. You can create the probability distribution. It's the chart with all the probabilities in it. After you have a probability distribution, you can always make a histogram. It looks like a bar graph, but the bars are touching. Another type of distribution besides uniform and symmetric is called a binomial distribution. And I think, again, you might have some fill in the blanks here. One type of probability distribution is the binomial distribution. This shows the probabilities for the outcomes of a binomial experiment. That doesn't really help me. I don't know what any of that stuff is. What is all this binomial business, right? Okay. So now we're going to talk about what is a binomial experiment. It has to meet the following conditions. There must be n independent trials. So that's kind of like the total of your sample space, how many trials you're running. Each trial will have only 2 possible outcomes: success, failure. This is why we call it binomial. So the prefix bi means 2. Okay. There are only 2 outcomes possible. So like in the last example when I was doing the distribution for the sum of the spinner, my random variable x was equal to my sum. I had more than 2 possible outcomes. I could have sum 0, 1, 2, 3, 4. That's not a binomial experiment. Okay. Generally, we reduce it down to successes and failures. Note that a success and a failure of a particular event are going to be complements of one another. Either the event happens or the event doesn't happen, right? Success, failure are my 2 options. The probability of success will remain the same for each trial. Remember, they're independent trials, so the probability of one trial does not affect the probability of another. And so you assume that the probability of success is the same for each trial. We're going to call that P. And then the probability of failure, because it's the opposite or the complement of success, is going to be 1 minus p. So the two probabilities, success and failure, always have to add up to 1. They're the only two probabilities allowed. They're going to add up to 1. And then we've got a formula. For a binomial experiment. The formula looks worse than it really is. It kind of reminds me, it's not exactly like binomial expansion, but in a way it's kind of like a binomial expansion problem, where if you like want to generate one term of that expansion, there's 3 parts. And that's kind of true here as well. There's 3 parts. One of them is a combination, and then the other 2 are your probabilities. I'll give you a minute to write it down. So I think this is a formula that I may provide for you on the test on Friday. So you don't necessarily have to memorize this one. And that's probably true a lot of times, even if you're taking a stats course, because if you have like all these different types of distributions, it's usually pretty tough to memorize all the different formulas for each distribution. Some of them you get to know pretty well, like you do it enough times that you sort of know it. This one would probably be an example of that. Okay, so I want to point out some things here. This is the probability for just one potential outcome in your binomial experiment. You've got n independent trials, right? But this is saying like of the n trials that I do, I have exactly k successes. So if I'm running 5 trials, this could be maybe like the probability of 3 successes. And then everywhere I see k, which is in each one of these parts, that's going to be 3. If there were 5 independent trials, everywhere I see n, that's going to be the number of trials that I did. And then the p's, remember, are your probabilities of success. So here you take the probability of success, you raise it to the number of successes that you have. And then this one, 1 minus p, is really just your probability of failure. It's the complement to p, right? And so it's the probability of failure raised to the number of failures. Okay. And then, of course, we have this like combination part here at the beginning. Okay, and that's, think about combinations. It's avoiding our repeating sets. Okay, so we're going to do a couple examples. And we hopefully will finish with a little bit of time for you to start your homework, because these problems generally tend to take a little bit longer, okay, just because the formula is longer. All right, find the probability of rolling 5 exactly 3 times out of 10, and I'm assuming that I'm talking about rolling a 6-sided dice. Well, we could say, like, what is the probability of rolling a 5, right? Once. What's the probability of rolling a 5? 1/6. So I'm going to say probability of rolling a 5, that probability is 1/6. But then it adds in this other piece about rolling the 5 exactly 3 times out of 10. And that becomes kind of an issue, like, okay, is that the first time, second time, third time, or the first time, second time, fifth time, right? There's all this at play. But this part right here, where I want exactly 3 out of 10 trials, those are going to be my n's and my k's. So how many trials am I running? 10. Okay. These are my number of trials. How many successes do I want? 3. So that's my k. Which means what about failures? There are 7 failures because there's 10 trials. So 7 times I don't roll a 5. What's the probability of not rolling a 5? Carson? 5, 6. Don't think too hard, right? If the probability of rolling a 5 is 1, 6, what's the probability of not rolling the 5? 5, 6 is all the other outcomes, right? It's way more likely that we're not going to roll a 5 and than to actually roll the 5. So we're going to set up our formula. Probability of 3, exactly 3 5s, like that. Okay, I'm going to do a combination of 10 choose, number of successes, which is 3, times the probability of success, which we said was 1, 6, and I raise it to the number of successes. So it's all about success, that second piece. And then the last piece is your probability of failure raised to your number of failures, which we just said was 5, 6, and number of failures. I didn't write it down. How many failures you going to have? 7. Okay, take a minute to think about this outside of that formula, right? Okay, the combination thing is n choose k. The total trials, choose your number of successes. Okay. But the last 2 parts of this, it's your probability of success raised to number of successes. Probability of failure raised to number of failures. Did you have a question?
Yeah. So, since the probability of failure is 1 minus p,
Uh-huh.
if p were greater than 1, would that be a negative probability?
The probability of p will never be greater than 1, because probability is never greater than 1. Does that answer?
Yeah.
The highest probability of success that you could have is 1. And then the probability of failure would be 0, because if it's absolutely going to happen, then it's not going to not happen. So that would be as good as it gets. Okay, type it into your calculators. I need everybody to make sure their calculators can work with the binomial distribution. Okay, so please type it in. I would say on these round to like maybe the nearest 100th or 1000th. That would be 2 or 3 numbers after the decimal. If you have to create a whole histogram, sometimes they can be pretty close, so having an extra third number might be really good. I'm spying on Mo, and she has 0.155. Can anybody second that? Jake is seconding. Okay, so everybody type that in. Make sure you can get 0.155. Call me over if you are not getting 0.155.
Well, this is also.
Where do you want to put multiply?
I think.
Yeah, you can do that. Yeah, because if you put the times right there, the calculator is going to follow the order of operations. So you can do your
It's always like
first.
the middle four.
It will follow
The first thing and the last thing.
The trouble would be if you wanted to
As
multiply
long as
an
you,
exponent, then
like,
you'd have
plot out
to
the
check
big
that.
picture,
Otherwise, you'd be
which
okay.
I did.
Yes, ma'am. Oh, your is this carrot button.
Not the shapes.
And then make sure when you type the rest of it that you click to the right so you're not in the exponent anymore. Okay. Not too bad, right? The hard part about some of these problems is, like think about the quiz that you guys worked on at the end of the class on Friday and all the different probability things. If this is just a random question mixed with other probability questions, how does it stand out to you that this is a time to use binomial distribution, right? Okay, so I think the thing that I'm always thinking about is if it is telling me a number of trials that I'm running and exactly how many successes, I'm going to be looking for that kind of phrasing. Okay, last example. Okay. This is probably more common, like what you're going to do the binomial distribution for. If you're taking a stats class or something like this is very common. So according to a survey, about 62% of adults have visited the dentist in the past year. You ask 5 randomly selected adults whether they have visited a dentist. So like, haven't you ever like just like had the TV on and you heard like a report about a stat? Like 62% of people have visited the dentist, okay, or something like that, or you know, X amount of Americans don't have health care, something like that. You hear stats all the time. Okay, so this is like us going out and we're gonna like test it and see what happens. So we're gonna go and ask 5 random adults if they have gone to the dentist. Okay. So we're running an experiment. If we talk to 5 people, that's our number of trials, right? We're going to do 5 trials. So we're going to ask 5 randomly selected people. So n is equal to 5. Whether or not they have visited a dentist in the past year, and what are their only answers going to be? Yes or no. So it's binomial. Okay, there's only 2 possible answers. I think we want to know if they have gone to the dentist. So that's going to be a success if they say yes. Okay. So let's let 62%, that's going to be our P. Okay, our probability of success. If our probability of success is 0.62, what's our probability of failure? 0.38. So if you want to jot that down, you can. Okay, and then this is asking something different. It's asking for the histogram. So remember, the histogram is our little chart. We put all of our outcomes on the horizontal axis. What's possible when I talk to those 5 adults? Yes or no? And like out of like all 5, what could happen?
100%
All 5 of them went to the dentist? What else could happen? None of them went to the dentist? Or 1, 2, 3, or 4 people went to the dentist? Some people are scared of the dentist. That's 6 different outcomes, right? So I have to calculate the probability for each and every one of those number of successes. Okay, so I'm going to leave myself a little bit of space over here. I'm going to do the probability that 0 people went to the dentist. So I'm just going to say P of 0. Well, that would be a combination of 5 choose 0. My total trials choose my successes. And then I'm going to multiply by my probability of success, 0.62, raise the number of successes, but this would be bad if I went and asked all 5 adults if they had been to the dentist, right? 0 successes right there, times my probability of failure, which you guys told me was 0.38, and this would mean if no one said they went to the dentist and all 5 people said, no, I didn't go to the dentist, so that's going to be 5 failures. Now type that in because I'm going to teach you, if you don't know how on your calculators, to go back so that we don't have to like keep typing in everything if we don't want to. I'm getting like a 0.008. That's a pretty low probability, isn't it? Less than 1%? 0.8%? But doesn't that make sense? Because the probability probability of adults going to the dentist is over half, right? 0.62. So if I'm going to talk to 5 different people, it's unlikely that all 5 of them are in that 38%, that less than half percent that go to the dentist. So it would make sense that the 0 doesn't have a lot of probability. Okay, now if you type that all into your calculator, I just want to point out to you that the setup for the probability of one person going to the dentist is very similar, right? What's the only thing that changes?
Exponents and like
Your choose and your exponents, right? Your n's or your k's and your n minus k's. So in your calculator, you need your number of successes to go up by 1. You need your number of failures to go down by 1. You can just click the up arrow on the little calculator. And if you click the up arrow, it takes you like back to your work, and you can just like scroll over the 0 and type a 1. Do that again, type a 1, scroll over the 5, type a 4. If you've got the graphing calculator, some of them will let you go up, some of them you have to do second enter, and it'll let you go up. But try that so that you don't have to retype everything. This is going to be handy if you're doing your tests, and you don't want to have to type in all those combinations again, because that can get tedious. Oh, it's giving it to you in scientific notation. Hit enter. No, stop it. 7.9 times 10 to the negative 3. So if you moved your decimal 3 to the left, 1, 2, 3, there would be 2 zeros. So you have the same answer. Yes, you just need to be able to read the scientific notation. I do not know on the Casio. You could Google it. Let's see, Abby got 0.065 for one success. And then you keep going down and do all of them. PF2, PF3, PF4. Brianna got 0.211. Let me know if you disagree. Or if you're having trouble. See, Dylan got 0.344. For the probability of 3, we're going to get a 5 in there too, don't we? And Mo got 0.28. For 4. Lauren got 0.092. 5. Are we doing okay on calculations? You know, that formula looks really terrible and scary, but the nice thing is, like if you're doing a problem like this where you need to create the distribution, you get a lot of practice with it, you keep reusing that formula and it is not so bad. Okay, so then you just have to create the histogram. Okay, so you actually have to calculate these. I'm okay with this on the test if you like maybe show a setup for one and then you use your calculator for the rest. It's just if you make a calculator error, I won't know what you're doing. Okay, so this is good to have at least one setup correct. Okay, what's my highest probability? 0.34, so I'm probably going to go by 0.1s. 0.1, 0.2, 0.3, 0.4, and I can draw it in. Now note that this one is very, very small, 0.008 or 0.01, so I'm just going to draw like something really low. And then 0.065, maybe something like that, 0.21, something like that, 0.34, something like that, 0.28, something like this. And 0.092 would be close to 0.1. So it's a little bit under that. You know, someone looking at that histogram might say it looks symmetric. It is a little bit skew. We actually say that this one would be skew left, which is like opposite what I think. But like where the tail is where you say the skew is. But this makes sense that like our taller bars are over on the right because remember, more people do actually go to the dentist. So it makes sense that the higher numbers have better successes. Can you answer the question for B? What's the most likely outcome? 3 people went to the dentist. In the last year. What's the probability that more than 3 people surveyed have gone to dentists in the past year? What will you do to calculate that? More than 3. Add the 2 for 4 and 5. If it's more than 3, it doesn't include 3, right? So that would be the probability of 4 or 5 had gone to the dentist. So probability more than 3. That's a 4 or a 5. So I would do like what? 0.28 plus 0.092. Whatever that may be. 27.372. Note that like when I'm calculating my probabilities, again, these are still like regular probabilities. They're never going to be more than 1. Okay. They're always going to be between 0 and 1. Alright, your homework assignment is only like maybe 4 or 5 problems, I think, in the textbook. Tomorrow is going to be an opportunity for us to work on binomial distributions again. So just kind of get comfortable with the formula. The rest of the week really, like we have our work day tomorrow and then a couple of days review and test on Friday. It's an opportunity for you to like let all the things about probability sit and try to get questions answered. But you'll have to make sure that you're participating so that you can kind of like see what are the different types of probability questions we can ask.